I'm very pleased to introduce Mel Hochster from the University of Michigan, who will tell us about embedding theorems for modules and behavior of closures.
Okay, thank you very much. And I'd like to thank the organizing committee for inviting me. Um, I guess this is the first time I've talked in this Fellowship of the Ring seminar, although I was, of course, on the committee for a few years. Um, the work I'm going to talk about is joint with Yongwei Yao, and we've had a version of this posted uh, for quite a while. We're going to come up with quite a new version soon with a bunch more results. In fact, there are two related papers. And I want to mention that websites at the University of Michigan are migrating. I put up my new website, which has the word sites in it. The old one is the same without the word sites. Last time I checked, they're still both available, but a lot of the links on the old one are broken and I can no longer access it to update it. On the other hand, I haven't transferred everything, and there are a lot of materials on the old site. Um, so this isn't working. Oh, there we go. Uh, so I'm going to talk about using embedding theorems for modules to get information about closure. And we originally started working on this aiming for theorems about finite projective dimension, but it turned out, and the operations that we originally were concerned about were tight closure and plus closure, but there are a lot more of these operations now, and these proofs work for a lot of the new closures as well. And I think the results on embedding have independent interest. And while some of it concerns finite projective dimension, it generalized to finite Gorenstein dimension or G dimension as well. And I should say, in their original paper, Auslander and Bridger only talk about G dimension. They never say what G stands for, uh, but everybody assumes that they had Gorenstein in mind, or at least uh, a lot of people assume it. And I don't think this notion is as widely understood as projective dimension. I checked with Carl, and I don't think anybody's spoken about finite G dimension in this seminar. And I'm going to talk about some of its basic properties. And I will post the slides after the talk. And I'm going to tell you that I won't actually cover all of the slides that are here. Some of them are meant to be read. Uh, and but if you are interested in more detail, some of them have more detail. And these references, there's a bibliography uh, at the end, which uh, if you look at the posted version of the slides, you can see what the references actually are. Um, so R will always denote an Noetherian ring. I will also be talking about some non-Noetherian rings, but R will always be Noetherian. And local will always mean Noetherian local ring. Um, and I'm going to use a small asterisk uh, for the dualizing into R. So it's not tight closure, but I will also talk about tight closure. So I'm going to use this large asterisk, which is bolder, and also it has 8 spokes instead of 6. So I think you should be able to distinguish it easily from duality. And now an R module G is called totally reflexive or in the G class if, first of all, the map to the double dual is an isomorphism, that's reflexive, but also all the x of G into R vanish and all the x of its dual into R vanish. So that's 3 conditions. Of course, projective modules have this property, and you can think of this as a weak form of being projective. And the term finitely generated Gorenstein projective would be used or just Gorenstein projective if finitely generated is understood for the same thing. And we'll see that you can also call them modules of G dimension 0, but technically I think most people give 0 G dimension -1 or minus infinity. So, and it is totally reflexive. And the reflexivity on conditions and the vanishing of X for both G and its dual are needed by a result of Jorgensen and Shega. And in general, one needs to check the vanishing of infinitely many X modules, even over an Artin local ring. So there isn't any criterion that says if all the X with M vanish and it's reflexive, and the first 10,000 times the dimension of the ring X with G star vanish, then they all do. There isn't a theorem like that, and there can't be. And as general references for finite G dimension, there's a book by Christensen and Adela Vracu has a survey in a volume dedicated to David Eisenbud. And there are many reflexive modules that are not totally reflexive. So, for example, if you take kill x squared and xy and look at the residue field, it's reflexive. The dual is isomorphic. If you hom into R, you get a copy of K back. Now, it is true from the definition that totally reflexive, if G is, its dual is, but not the converse. If the dual is totally reflexive, then the double dual is, but not G. For example, you can start out with R plus a torsion module over a domain. That's not reflexive even, but when you take the dual, you get R, and that is totally reflexive. So I'm going to talk about several properties of totally reflexive modules briefly. One of them is that if you have a short exact sequence and the rightmost module is totally reflexive, then G and G prime, the other two, one is totally reflexive if and only if the other is. And the dualization functor is exact on exact sequences of totally reflexive modules. And I'll mention that a module is called torsionless if the map to its double dual is injective, and that's equivalent to it embeds in a possibly infinite product of copies of R. And I'm somewhat interested in that notion, even if the module isn't finitely generated. And that term was introduced by Bass about 60 years ago, I would guess. And of course, sorry, reflexive implies torsionless, obviously. And so totally reflexive implies torsionless. Now, a finitely generated torsionless module just means that G is a submodule of a finitely generated free module. But, and if you have finitely generated and the ring is a domain, torsionless is torsion free. But in general, it's quite different from being torsion free. For example, the rational numbers, that's not torsionless over Z because hom of Q into Z is 0. There are no infinitely divisible elements in the integers. And local ring of depth 0, whatever you think about torsion, it's not it is torsionless as a module over itself. Any ring is a torsionless as a module over itself, no matter how many zero divisors it has. Whoops. But the non-zero divisors in R are non-zero divisors on the torsionless module. And this totally reflexive property is local on primes or on maximal ideals. And in the Gorenstein case, a totally reflexive is equivalent to maximal Cohn-Macaulay module. So there are lots of totally reflexive modules that are not projective. It's a much larger class. Now, you can't do arbitrary base change, uh, but of course you can if the Tor dimension of the ring is finite, you can do base change. Totally reflexive modules are homologically trivial against modules of finite Tor dimension, even non-Noetherian modules of finite Tor dimension. Any questions so far? Guess not. And of course, flat is certainly okay for that. And please remember the notation M sub S for base change, because I use that a few times later. And an important example is if you have a regular sequence in R, it will be a regular sequence on G, and G mod XG will be totally reflexive over R mod, the regular sequence. In that respect, it's like modules of finite projective dimension. And in fact, the converse works in the local case, provided you assume the sequence is regular on both R and G. And faithfully flat, tensoring with faithfully flat doesn't disturb this property. And in the local case, if G is totally reflexive, its depth on the maximal ideal is the same as the depth of the ring on the maximal ideal. And so what we're going to do is explore the class of finitely generated R modules with a finite left resolution by totally reflexive modules. And these include modules of finite projected dimension, but many, many more. So by the G dimension, and for M is 0, it'll be -1 or minus infinity if you like. And it's the length of a shortest left resolution by totally reflexive modules. So I haven't shown M. M is the augmentation. So this complex is acyclic, and H naught is M, just as you would talk about finite projective dimension. This is quite similar. And if there is a finite resolution, and otherwise the G dimension is plus infinity. So that's a very natural and straightforward generalization of finite projective dimension. So G dimension at most 0 is equivalent to totally reflexive. If the projected, everything of finite projective dimension is obviously of finite G dimension, but what's not obvious is that G dimension doesn't ever get smaller. If the projective dimension is finite, they're equal. And I'm going to run through some properties that are all parallels of properties of finite projective dimension. So if the G dimension is less than or equal to n, if and only if the nth module of syzygies is totally reflexive. Of course, if you had projective dimension, the nth module of syzygies would be projective. And if you have an exact sequence and two of the modules have finite G dimension, so does a third. And you get the same kind of results as you do for finite projective dimension. So in particular, when the projective dimension, or the G dimension of M is bigger than M double prime, the kernel has G dimension exactly one less. Did I say projective dimension? Anyway, I should have been saying G dimension throughout. And that means when the G dimension of D is at least 1, if you take a module of syzygies, it drops exactly 1. And if you make a flat base change, the G dimension can only go down. And the G dimension, whether it's less than or equal to D, can be tested locally. And if you have a regular sequence on M, on R, sorry, if you have a regular sequence in R on M, and uh, you can form the quotient, and the G dimension is at most the same, and it doesn't change if R is local. And also you can test for finite G dimension. Uh, when you know that the G dimension is finite, you can test what it is by checking X against R. But you have to know it's finite. If you don't know it's finite, testing against R isn't enough to give it to you, as I commented about earlier. Um, and the following is very similar to the Auslander-Buxbaum-Serre theorem. So if you have a local ring of dimension n, R is Gorenstein if and only if the G dimension of the residue field is finite. That's similar to projected dimension, but now you have Gorenstein instead of regular. And if it's finite, it will be the dimension of the ring. That's just like projected dimension. And if and only if every module, so in the Gorenstein case, every module has finite G dimension, and they're all at most n. So this is very similar to the situation for finite projected dimension. And you also get something just like the Auslander-Buxbaum theorem, which conveniently is the Auslander-Bridger theorem, so it's still AB if you're into abbreviations. And so if R is local and the G dimension is finite, then it's the depth of R minus the depth of M. So that's exactly like projective dimension. Uh, again, I've been going pretty quickly, but if you've never seen G dimension before, I hope uh, this will show you it's an attractive theory. And since every module has finite G dimension in the Gorenstein case, uh, it's pretty useful. Um, have there been any questions at this point? Okay. So if R is Cohn-Macaulay with canonical module omega, then omega has finite G dimension if and only if R is Gorenstein. So this is, I think, an interesting example. So suppose that R has Kroll dimension at least 3 and is Cohn-Macaulay but not Gorenstein. And suppose it has either an isolated singularity or just an isolated non-Gorenstein point. So the only prime where you localize and it's not Gorenstein is the maximal ideal, M. Then the canonical module will be reflexive because you can test that in codimension 2. And when you localize at any prime of height 1 or 2, uh, you'll be in the Gorenstein case. But so if you, uh, but the canonical module is never totally reflexive if the ring isn't Gorenstein. And here's a completely explicit example. Suppose you take a 2x3 matrix of indeterminates and kill the 2x2 minors, which is also the same as the Segre product of a polynomial ring in 2 variables and a polynomial ring in 3 variables. And the ideals generated by SU and TU, or if you like, any column of the matrix, if you think of it as uh, entries of a matrix, is a canonical module. And these will be reflexive, but not totally reflexive. So there's a nice change of rings theorem for G dimension. And by the way, this is not, if you if you're one of the people who likes to just read the theorems and prove them all for yourself, you might like a little bit of a challenge with this one. It's not so straightforward. But if you have a regular sequence in the annihilator of the module, M has finite G dimension over R, if and only if M has finite G dimension over R mod X. It's a module over both. And this is different, very different from projective dimension, which doesn't have this property at all. For projective dimension, you need that the regular sequence is also part of a minimal set of generators for M, and then it's true. And you have this relation that the projective dimension is K bigger over the ring. And now I'm going to state the embedding theorem, which is the result I want to apply. Uh, so I want to call a module regular cyclic if it's the quotient of the ring by an ideal generated by a regular sequence. So X with underlined represents a sequence of elements that's a regular sequence of the ring. And X is allowed to be empty, in which case the ideal it generates is zero. So we're allowing N to be R. R is also a regular cyclic module. Is there some other term for this in the literature? Does anybody know? Uh, I assume the host would let me know if anybody answered.
No one in the chat.
Okay. It seems like a natural thing to define. Anyway, here's the theorem. And we've had this theorem for quite a long time without, and posted it without actually publishing it, but we are getting it ready to publish now. But it's been up on at least not on the archive, but on my webpage for quite a long time. So let R be Noetherian and assume that M has finite G dimension, D. Then there's an integer H, and there's an exact sequence. So this is the embedding. M is embedded in D, where D is a direct sum of regular cyclic modules. So D is a direct sum of quotients of R by regular sequences, which is a very nice thing to have for M. But not only that, you can take all of the regular sequences, if you like, to be initial segments of a single regular sequence. And the quotient also has finite G dimension, no bigger than D. So you see, just looking at this, if you know about D and C, you know that M has G dimension at most D just from the exact sequence. And if you have finite projected dimension, you also have all the same. This is the original version of the theorem was for finite projective dimension, and then we generalized it to G dimension because we originally were just conjecturing it for finite projective dimension. So, and I'm not, the proof is a very, very long and uh, sort of many piece induction. It's convoluted, but I'm going to say a little bit about one idea in the proof. Oh, a couple of comments first. If M is zero, take the empty sum. And if you don't like thinking about G dimension, you can think only about projected dimension if you like. And oh yeah, the sequence shows that this I commented already. The G dimension of M is at most D. Notice the corollary, if the G dimension is finite, all the associated primes of M are associated primes of regular sequences. That's obvious from the embedding. Uh, I don't know if this result is in the literature. So if anybody has a comment about that, I'd be interested. Because I assume there are people in the audience who are more expert about G dimension. I'm mostly a user, not someone who has done a lot of research about it. Um, Although I did look at almost every paper I could find on it at one point or another. Um, so I'm going to give hints about the proof. So when a module, I want to comment that when a module has finite projector dimension or finite G dimension, there are regular sequences lurking in its presentation. And that's a somewhat vague sentence, but it is a key point in the proof. And I'm not going to go into it too much more, but I'm going to talk about uh, acyclicity criteria, and it will perhaps be apparent then. And the second hint is over a field, every matrix can be diagonalized. And manipulating matrices over a PID, every matrix can be diagonalized. So in fact, over a PID, every module is a direct sum of regular cyclic modules. You don't have to embed, it really is a direct sum. You can think of this theorem as a generalization. You can't hope that every module of finite G dimension is a direct sum of regular cyclic modules, but you can hope that it's embedded in them. And uh, you can, if you're familiar with a proof of this by manipulating matrices, uh, it's a hint. And to find the embedding, you just manipulate the presentation matrix sort of with elementary operations. Uh, well, that's kind of an exaggeration, and there's a slight problem. You can't divide by an entry in the process of clearing a row or column, and you can't get ideals to be principal and get a generator of the ideal spanned by the row as an entry, which you can in the PID case by so there is a problem. But I'm going to talk about one of the tricks for handling this. And to do that, I want to talk about the one by one case, which you may think is not very interesting, but
Well, there is a question that just appeared in the chat.
yeah,
In characteristic P, if G has finite G dimension, is the G dimension of G and any G resolution of it invariant under the Frobenius functor?
no.
Okay.
Uh, I said that very quickly, but I think that's almost equivalent to finite projected dimension, right? Being that's what I think off the top of my head.
Okay.
Um, so what happens to a one by one matrix when you multiply its entry by a non-zero divisor? So if you're thinking about the co-kernel of the matrix A, I'm not assuming anything about A. It becomes the co-kernel of U times A, or R mod R times UA. And R mod AR is isomorphic to RU mod RUA because RU is still a free module on one generator. And that embeds into R mod RUA. So what happened when we multiplied by a non-zero divisor was that we embedded the module co-ker A into the bigger module, a co-kernel of UA. Well, now suppose you can manipulate the entries of a presentation matrix and get just one non, maybe you do it with just the usual elementary operations which don't change the co-kernel. And suppose you can get a non-zero divisor in the presentation. And of course, you can permute rows and columns and get it in the upper left corner. Well, if you can do that much, what happens to the co-kernel when you multiply a whole row by U? Well, I'm going to leave it as an exercise, but you get a presentation matrix for an extension module. It's like you're killing a submodule of a free module, and the submodule doesn't change, but it's like taking one of the generators of the free module and dividing it by U to make a bigger free module. So that's what happens. So here's the matrix. Let's say there's U, and then there's the rest of the first row, and there are the other rows. And then you can multiply the second row by U and the third row and all the rows each time you're extending the module. And in the first column, all the entries are now divisible by U in the extension module. So there's a focus on the first column. And now you can do what you wanted to do. You can clear, there's that column. You can clear the first column by honest row operations. Whoops, too far. And get all zeros there. And you've got a simplification of the matrix where a whole column is zero. You still have U in the upper corner. Uh, and that's one idea in the proof. And uh, there are a bunch of others, but it would take a whole 2-hour talk to go through the whole thing. But by a very careful induction, uh, you can get this idea and a bunch of others. And I say this idea also occurs in earlier papers by Dutta, and there's also a beautiful paper of William Smoke. And while the details look complicated, the basic idea is elementary, if you'll forgive a pun on elementary operation. Anyway, before applying these results to closures, I want to talk about tight closure theory briefly and also about acyclicity. And I'm going to say on discussing tight closure, uh, some results may assume the ring is reduced and locally excellent without making that explicit. I've made it explicit, I think, almost all the time, but just in case. Um, so I'm going to tell you that tight closure is a useful operation on submodules. And if you're not very familiar with it, think first about ideals in R, originally defined in characteristic P. And it's small. If R is regular, everything is closed. And it's also big. I put that in quotes. It's not very big, but it's big enough that when you have a system of parameters, and so x1 through xk is part of a system of parameters, and so is it still when x is really xk plus 1. It's like the next parameter. And then the colon is inside the tight closure of I. So uh, this fact turns out to be an extremely powerful tool that it captures colons. And it also captures what the extra elements you get if you expand, take a ring that's module finite over R and expand I to it, and then contract it back to R. That's what you get is inside the tight closure. And in fact, I'll comment now, I'll come back to this. Pretty often it's equal if you allow every choice of S. And tight closure yields easy proofs that direct sumends of regular rings are Cohn-Macaulay of the Briançon-Skoda theorem, and the direct sumend theorem that every regular ring is a direct sumend of every module finite extension. And in fact, something better, every ideal tightly closed in R implies R is a splinter, which means R splits as an R module from all module finite extension rings. That's the definition of splinter. And so regular rings are splinters. That's the direct sumend theorem, which has only recently been proved in mixed characteristics. Now, under mild conditions, if you make a base change, uh, it preserves tight closure in the sense if you start with something in the tight closure of N, after the base change, it's in the tight closure of the image. And a lot of conditions that on tight closure and closely related notions imply or are equivalent to a good kind of singularity. And and because tight closure depends on Frobenius, this leads to the use of a lot of F words. Uh, for example, if every parameter ideal is tightly closed, that implies R is Cohn-Macaulayan normal and is called F rational. And that's close to the condition of having rational singularities. Uh, and I'll also note that time closure results usually come down to the domain case. Um, and very often they're stated with reduced, but one immediately reduces to the domain case. Uh, any questions at this point? Okay. So the definition looks technical. I haven't given the definition, and I won't. And it's often hard to calculate. But it does, and it doesn't commute with localization, so it has a few disadvantages. However, it does have a great many uses. Now, I want to talk about a theorem that's due to Karen Smith that's very important. So let I be a parameter ideal in a reduced locally excellent ring. Then U is in the tight closure of I if and only if U is in IS intersect R for a module finite extension. So this is what I mentioned briefly earlier. You can recover the tight closure from by expanding and contracting. Here, parameter ideal means I is generated by part of a system of parameters after one localizes. That's backwards. It should have been at any prime containing I, not the B should have been a P in the text file. P it contains I. Of course, if P doesn't contain I, uh, localizing blows up, I blows up to the unit ideal. And in the domain case, which is a central case, one can phrase this differently. So for an arbitrary domain, R plus is called the absolute integral closure of R, and it's the integral closure of R in an algebraic closure of the fraction field. It's the biggest domain that's an integral extension, and it's unique up to non-unique isomorphism. And so Ian Auerbach proved the following extension of Karen Smith's theorem. So if R is F rational, so that all parameter ideals are tightly closed, then whenever the projective dimension of M mod n is finite, the n is tightly closed. So not just parameter ideals are tightly closed, but everything where the quotient has finite projective dimension is tightly closed. And even when you don't have F rational, if R is reduced and locally excellent, when this quotient has finite projective dimension, then the tight closure is equal to the plus closure. And Ian's proof uses homotopy of maps between Gazul complexes and projective resolutions after not just the original in the original setup, but after applying iterates of the Frobenius endomorphism. So it's sort of linked to tight closure theory. So the embedding theorem. Oh, and I should also say, Ian proves a stronger phantom version where you have phantom projective dimension. I'll talk about that later. Uh, but we're going to use the embedding theorem to give proofs that aren't so closely linked to the use of the Frobenius, where the work comes in and proving the embedding theorem, and then the proofs become extremely easy, actually. So I want to talk about some acyclicity results. And because I'm interested in having them in a non-Noetherian case, I want to talk about depth and the depth of a module on a finitely generated ideal. So for the moment, I'm suspending the Noetherian assumptions. So R is not Noetherian, R is no longer Noetherian, but I is finitely generated. I'm not going to stick with that. And this will agree with the usual definition of depth in the Noetherian case. And this is the Cazul depth of M on I, also called K depth. So it's plus infinity if all the Cazul homology modules vanish. And, and otherwise, it's the least integer d such that hn minus d of fm is not zero, Cazul homology. So the Cazul homology vanishes uh, at the top, the first d of them. So depth zero would mean that the top Cazul homology is non-zero. Depth one, that the top Cazul homology vanishes, but the next one doesn't, and so forth. And of course, by the way, you can say this in terms of Cazul cohomology. Maybe that's more natural, but for historical reasons, I'm going to stick with this. And it's independent of the choice of generators of I. So this theory is now in the non-Noetherian case. It's unaffected by faithfully flat extension. And when it's finite, you can't find regular sequences if you just stick with R. But if you make a large enough faithfully flat extension, for example, a polynomial ring in n variables over R, it's the length of every maximal regular sequence in after you make the faithfully flat extension. So, and but I want to caution you in the non-Noetherian situation, the K depth can be finite even though the ideal times the module is equal to the module. So for example, if you join 1 over x and mod out by k of x, it's really the first local cohomology with support in x. Um, this x times m is equal to m. This is divisible. Uh, but the first h1 of xm is k. So the depth is 0. It's finite for this non-Noetherian module. And I'm now going to tell you a criterion for acyclicity, which is identical with the Buxbaum-Eisenbud criterion in the paper, What Makes a Complex Exact, ex except that K depth replaces depth. Oops, went too fast. Oh, let me mention that for references, uh, there's an exposition of this criterion in Northcutt's book on finite free resolutions, and I'm hoping to include this in a joint manuscript with Craig that's under revision. Uh, so let R be any ring, and G dot is a finite complex of non-zero, that's important, finitely generated free modules. And GI is RBI here. And N is any non-zero module. And I'm going to use alpha I for the matrix of the map originating in GI, and Ri for the determinantal rank of alpha I. But calculated mod the annihilator of the module. So, but I'm mainly going to be using this where the module has no annihilator, uh, but it works in this generality. Then when you tensor with n, it's acyclic if and only if the following two conditions hold. So one is that the ranks of the incoming and outgoing maps for any of these free modules is the same as the rank of the module. That's the same condition you need for exactness in a finite complex of finite dimensional vector spaces. And the k depth of the module you're tensoring with on the ideal of rank size minors for the ith map is at least I. So there are those regular sequences. You don't get finite projected dimension without there being regular sequences in the ring. And here they're hiding in the whole resolution, not just the presentation matrix, but uh, you do get depth at least one even in the presentation matrix for the ideal term by the entries. So actually, let's take that time for a 5-minute break, isn't it?
Yes, that sounds great. Let's.
Is I'm not going to take. I'm not. I think I will finish by 6:15 or so, and maybe sooner. Uh, but I think the break's a good idea anyway.
Okay.
Uh, questions, right?
Sorry. Go ahead.
I was just going to ask if there were any questions at this point before we take the break. Yeah, I'm not used to speaking at length anymore. My voice is giving out, but uh, I guess I'll make it through the talk. Okay, so we'll be
Sounds
back
as
in
though
5 minutes.
the embedding theorem is quite algorithmic. Have you actually made code?
Oh no, uh, yeah, you're welcome to look at the actual. The proof is up. I'm sure it's up on at least my old web page, so you can look at it. Uh,
Oh,
I don't think it's as algorithmic as it may have sounded uh, in the talk. I mean, there are a lot of difficulties that I've swept under the rug. Okay. Uh,
I'm pausing.
I stopped in the middle of a sentence. Uh, so phantom acyclic will mean, for the purposes of this talk, that you have that same rank condition, but instead of assuming depth, I'm just going to assume that the heights of these ideals, but I'm only going to do this uh, over a domain. If you don't have a domain, you have to worry about the height mod every minimal prime, and it gets kind of technical. Uh, and so in the case where you just have a free, it looks like a free resolution, uh, if it satisfies these conditions, it's not actually acyclic, but we call it a phantom free resolution. I mean, I mean Craig and I. That's started with tight closure in the uh, characteristic P case, but uh, we can talk about phantom resolutions in this generality. In the case of tight closure, uh, in prime characteristic P, if R is reduced and locally excellent, then for I bigger than or equal to 1, in every one of the free modules, the cycles are in the tight closure of the boundaries. So if you think of tight closure as small, it means that cycles are close to being boundaries. And so the uh, homology of the complex is fragile in a certain sense, like goes away if you tensor with a regular ring or a ring in which every module is tightly closed. That's the origin of the idea. But we're talking about it in greater generality now, even mixed characteristic, when you have these conditions. So I want to talk about just an abstract closure operation on finitely generated modules over an Ethereum ring. And so it's going to assign, whenever you have an inclusion of finitely generated modules, the closure will be something in between the submodule and the big module. And I'm not going to assume very many properties. There's quite a list of possibilities, but I'm only going to assume three conditions. But let me mention when the ambient module is the ring itself, so you're talking about closures of ideals, it's often omitted. So, and of course, if the closure is the module, we'll call it star closed. So here are the three conditions that a module is equal to its closure if and only if 0 is closed in the quotient. So this is true of tight closure and many other recent closures. And second, if you enlarge the module, if you enlarge the ambient module from M prime to M, the submodule stays the same, the closure only gets bigger. And the third condition is that if 0 is closed in each of two modules, then it's closed in their direct sum. So those are all things that are satisfied by tight closure, and actually by a lot of other closure operations. So examples of closures that satisfy these are tight closure, plus closure, solid closure, Frobenius closure, integral closure of modules, at least for some definitions. There are a lot of different definitions for that one, and various module and algebra closures, including Big-Cone-Macaulay algebra closures, extended plus closure, limb closures that Barkov, Baden, Linchuan, Ma, and I have recently introduced, and many others. So I'm going to call a ring star rational if every parameter ideal is closed. And it's suggested by the use of the term F rational. And suppose you have an Ethereum ring and a closure operation that satisfies those three conditions. So that's a fairly mild assumption. And suppose that for every regular sequence, the star closure of the regular sequence is the regular sequence, which is the same as saying that 0 is closed in the quotient in the regular cyclic module. So this would hold star rational as I've defined it, it would be for parameters as well. But right now, this theorem is only about, I'm just assuming the condition for regular sequences, which is weaker on the face of it. Then whenever the quotient has finite G dimension, not just projective dimension, but G dimension, it's closed with respect to the operation. So this generalizes, this is going to generalize Ian Auerbach's theorem in a somewhat different direction. But it's not, because I'm assuming, I'm not assuming, he has a theorem for the phantom case. I'll talk about that a little bit. And here's the proof. M mod n embeds in a direct sum of regular cyclic modules. And in each of these, 0 is closed. That's it. So with those three axioms, because 0 is closed in the direct sum of regular cyclic modules, M mod n is in there, so 0 is closed at M mod n. So the proof could hardly be easier once you have the embedding theorem. Any questions at this point? Okay. So the embedding theorem can also be used in the reduced locally excellent case to prove the existence of uniform test exponents in tight closure theory. And I'm not going to talk about, if you know what that is, fine. I'll just comment that sometimes a priori in doing a tight closure test, you have to check what happens with P to the E for all E, but sometimes you can bound what you have to test. And that makes it computation more feasible. But that's for the case of finite projective dimension. And there's also, Yongwei and I have a result for the phantom case for systems of parameters. And that an early version of that paper is also posted. But these results are not true if you only assume finite G dimension. You need finite projected dimension. And that's because of the Brenner-Monsky. We know that because of the Brenner-Monsky counterexample to localization. Tight closure doesn't localize, and their example is Gorenstein. In fact, it's a hypersurface. And in a hypersurface, every module has finite G dimension. So that's going to imply that when you have a test exponent, you have localization. So you can't prove any very general theorem on test exponents. It would give you localization in an example where it can't happen. By the way, this is very well known for tight closure, but it's obvious from the theorem that in a Gorenstein ring, if every ideal generated by a regular sequence is closed, then every submodule of a finitely generated module is closed, because everything has finite G dimension. So that's a different perspective on a theorem that's proved usually by other methods, by reduction to the finite length case. So I next want to just talk briefly about big cone Macaulay algebra closures. And so by a big cone Macaulay algebra or module closure, I mean the following. You have some class of big cone Macaulay algebras. It might just be one, or big cone Macaulay modules over R. Or you might assume instead also that the class is directed in the sense of given any two algebras in it, they both map to another algebra in it, or the same in the case of modules. So a mild directedness condition. And so then if you have finitely generated modules, you can define a closure as there are two things you can do. You can make the condition for every, I'll say algebra for simplicity, for every algebra or for some algebra. That is, that you make the condition that the image of U times anything in the big cone Macaulay thing is 0 when you go to B tensor M mod N. So the thing is, if you have an algebra, you don't have to worry about everything. You can just do it for one tensor U. So this is as B varies in the class. So depending on whether you're taking intersection or union, one case you're requiring it be in every, go to 0 whenever you map to B, and or you can just require that it go to 0 for some object in B. That modulo is messed up, obviously, but anyway. This is a different description of the same condition. And so for Bickholm-Macaulay algebras, it's just it's the same as the condition on one tensor U. And for ideals, J is contained in this closure of I if and only if for every algebra or module, IB equals JB. And in the case of an ideal, this closure is the intersection or the union of the contractions when you expand to a Bickholm-Macaulay algebra. Okay. Oh, sorry. That was in case I was running out of time. That was a short version of the previous two slides in case I needed it. So Bickholm-Macaulay algebras always satisfy the conditions 1 through 3 that I discussed earlier. So if R is a local domain of prime characteristic P, and it's either excellent or a homomorphic image of a Gorenstein ring, then R plus is a Bickholm-Macaulay algebra. So that's in a paper that Craig and I wrote. And then for the excellent case, the Gorenstein case is in a paper that Craig Hunicke and Gennady Lubeznik wrote later on, which is really in some sense, it's a better proof. I mean, it's more digestible. And that means that R plus is a Bickholm-Macaulay algebra closure. Sorry, plus closure is what I meant to say. If you take C just to be R plus, you get plus closure. That's a Bickholm-Macaulay algebra closure. And interestingly, over a complete local domain, it turns out that type closure is also a Bickholm-Macaulay algebra closure. We can, in fact, do it with just one Bickholm-Macaulay algebra. Or you can use every, either one. So here's a comparison theorem. So suppose you have a local ring and you have two closure operations, which I'll call them hollow star and solid star. And solid star satisfies 1 to 3, and hollow star is a Bickholm-Macaulay algebra or module closure. And for every regular sequence, solid star is contained in hollow star. So this abstract closure is contained in the Bickholm-Macaulay algebra closures, say. And if you have finitely generated modules where the projective dimension is finite, then the solid star closure is inside the Bickholm-Macaulay algebra closure. And you can do this. This applies in particular when the solid star is tight closure and the hollow star is plus closure. So and you always have for those two, in that case, you get Auerbach's theorem as a corollary that plus closure is the same as tight closure. Just using the embedding result and this theorem of Karen-Smith. And again, you can't extend this theorem to G-dimension finite for the same reason, because in the Brenner-Monsky example, you get an ideal whose plus closure isn't equal to its tight closure. it can't be true for all ideals in that ring, or you'd plus closure commutes with localization. And in the Gorenstein ring, every finitely generated module has finite G dimension. So you can't get too optimistic. Now, Ian also proves the result when the quotient has finite as a phantom resolution. And Yongwei and I also have a way of getting similar results with embedding theorems in the phantom case. But there are all kinds of new issues. Our embeddings aren't actually true embeddings. They're phantom embeddings in a sense, in which the kernel is in a tight closure. So that's a whole new set of complexities, and I'm not really going to focus on that here. But there's one point I do want to make that comes up in the phantom results. Phantom resolutions become acyclic when you tensor with a big cone Macaulay module or algebra. Anyway, so one corollary of this comparison theorem, by the way, I haven't proved that comparison theorem. Proof is very short, and I'm going to give the proof because it is very short. But it implies that if two cone Macaulay closures, whether they're algebra closures or module closures, if they agree on ideals generated by regular sequences, they agree whenever you have finite projective dimension. So this is the proof of this comparison theorem. So you can pass to the quotient, and you can assume, therefore, that n is 0. And then you embed, this m is the old m mod n. You embed n in a direct sum of regular cyclic modules, and note that the projective dimension of C is finite, because it's the projective dimension of C that's going to be crucial here. And you can take a finite free resolution of C, because it has, and by the general acyclicity criterion, which is this non-Noetherian version of the Buxbaum-Eisenbud criterion, the depths on the big cone Macaulay module or algebra are bigger than or equal to the depths of R on the same ideals. So regular sequence on R implies regular sequence on B. And if you're in phantom case, having big enough height will give you the regular sequence in the big cone Macaulay object. So that means that the tensor product of G with any of these big cone Macaulay, I'll say algebra for simplicity, they're all acyclic. So the torus against B all vanish. And that implies, because of the short exact sequence at the top, that when you tensor with B, you get an injection of B tensor M into B tensor D. When you go up to the big cone Macaulay algebra, that tensor product injects. And now basically you're done. The result now follows from the fact that if an image in B tensor M vanishes, this is messed up, then it vanishes when mapped further. It should say it vanishes when mapped further to B tensor D. There's a phrase omitted here. Oh, no, maybe it's right. Sorry, it is right. If an image vanishes when mapped further to the direct sum of cyclic modules, it must have already vanished in B tensor M, because the mapping is injective. And so that's it. So thanks for listening. And any questions? Hello?
Yes, we can hear you. Sorry, I was just waiting for the applause to Yeah, yeah. Actually, if there's no other questions, could you go back to that statement about the containment of the star closure from BCM, like the BCM closure versus the yeah the one that
Yeah,
I just want to yeah
this one.
this one. So that and then the next statement the conclusion.
Yeah, sorry. I by the way, you may have noticed I have 275 slides according to preview. But of course there are a lot of that's because of the pauses and special effects.
So let's see. It's just in the projected dimension finite. So I was just trying to think
I
like
suspect you'd like a phantom case
yeah,
where you have parameters instead of regular sequences.
sure. But
Uh, so
but
that
three only being for only regular sequences are already a very strong statement, right? You don't need it for parameters. You just need it for regular
for
sequences.
this for projected dimension, right?
Oh, I see, I see. Oh, but for the phantom one, it's for parameter. The condition three is a parameter type condition.
Right, because
Okay,
uh, right.
okay.
So you can, but we the the version of the phantom paper that's posted is quite old and it's kind of a stub. I don't know what else to call it. It doesn't contain a lot of things that we think we can do now. We'll see when it's all actually written. Um,
I see. Okay. Huh.
so these embedding theorems really
Yeah, it's very powerful.
are powerful, and uh, I mean, it's kind of hard to prove the embedding, but it's then very easy to prove the comparisons. Um,
Maybe I should ask, are there other questions from the audience? Okay. Hmm.
uh, I will mention that for the version that I'm going to put up uh, on the web, there are quite a few references in that version that
So
I mean, everything that I referred to during the talk is in here somewhere, I believe.
for the phantom version, if
Yeah.
let's say you're comparing two big Coma-Macaulay algebra closures, right? Like R plus
Okay.
and like tight closure, or just something else I know is a big Coma-Macaulay algebra closure, um, or like a mixed characteristic one. Um,
Yeah.
uh, is there a phantom version where it's like phantom with respect to like that B or something? Because I can imagine, you could talk to phantom instead of doing like the usual
It, sh-
phantom.
it, there, there should be, but what we think we can do isn't really written down.
Okay, okay,
Because the version that exists was written thinking about uh, actual tight closure and plus closure.
it's
So I need to be cautious in answering.
okay, okay.
Yeah, I'm aware. We're going to look at your question that you sent me.
Well, that question is hard because we don't have Karen's result, but
Right.
um,
Uh,
or that's an additional difficulty.
yeah. Yeah.
Okay, well, if there's no more questions, I'm going to pause the recording and we can all chat freely, I guess.